Okay, here we are. We're almost halfway down the term. By the end of this lecture, we will be halfway down the term. We've introduced some really cool topics so far, and we're now done probably, I think, the hardest part of the term. Some people struggle with this lecture because it is an entirely new concept for most people. But I think it's kind of fun. We don't do very complex calculations with this one, but I do introduce some new concepts to you. Now, I'm going to warn you, I am a little bit sick. I now have what my kids had last week. In fact, the daycare we have has been declared an outbreak, not of COVID, but an outbreak of whatever this is, meaning like they had a third of the people there yesterday. My kids were finally able to go back to school yesterday, but I am running on no sleep. I'm sick, and I am so behind in work that I feel like I'm gonna cry. So basically, I feel like all of you feel right now, I'm sure. So I do get it. I remember that feeling when I was a student, that it just felt so overwhelming all the time. And I can't imagine trying to do this through COVID. So I'm not asking for your sympathy. I'm simply asking for your understanding. Okay. Oh, I don't even have the slides up for you. Let me just pull this up for you. Okay. I have to just swap these slides around for a second. Okay, so here is our lecture for today. It's the principles of stress and strain. I used to hate teaching this particular lecture. I always really struggled with trying to communicate these concepts, but over the years, it's turned into one of my favorite lectures to give. Mostly because, especially when I gave it in person, I found the students really engaged. This is one that, in some ways, is the most intuitive and least intuitive simultaneously. I'm also going to warn you that it is 5 a.m. and my kids hopefully stay asleep throughout the recording of this lecture. Because I still have to be in the city on Thursdays. I basically have to double down on my time. So my whole Thursday is still in the city being there, but I have to pre-record the lectures. Okay, so today we're going to give a quick refresher on the types of forces, and then I'm going to introduce stress and strain to you. Like I said, in some ways they're very intuitive, and in some ways people struggle with them. So some of it is going to be me trying to find ways to talk about these issues and relate them to things that you do intuitively understand in your life, because you work with and experience stress and strain all the time. And in fact, they're terms that end up in the everyday lexicon or use of words that you don't even really realize are talking about these exact principles. Then we're going to see how stress and strain are related to each other, and that's where we talk about modulus of elasticity. And then I'm going to talk about how we can actually graph what these things mean and what takeaways we can get from that relationship. Okay, let's, like we do often, refresh quickly the types of forces that we have. Remember, axial is compression, where we squish, and I'm showing you the little lines on my foam block, and then tension is where we pull. Tension is kind of hard to do with a foam block. It's maybe better with a hair elastic. We can stretch it out. Shear is the force acting in a direction parallel to a surface or a plane or cross section of a body. Basically, if we have two planes and we slip them by each other, it's what's happening at that interface as we slip past each other right there. If those two planes are far enough apart from each other, when we shift them relative to each other, we get a racking effect happening. Basically what we're saying is there's a series of infinite planes in between those two. Or as you can see, if we shear two planes far enough apart from each other, look at that. There's some force and some distance relative to each other. So as much as there's shear between these things, it's like it's shifting relative to each other. Bending moment. When we bend something, it's putting one side in compression and one side in tension. You can see the top is kind of squishing there and the bottom is stretching. If I bend it in the opposite direction, the top is stretching, which is tension, and the bottom is squishing, which is compression. So it seems like a lot of things can be, or at least bending, which we found quite complicated, can be related back to tension and compression. And remember, we saw that when we talked about trusses. A truss and a beam, both of them could be in bending. For an element, a beam, we talked about that internal bending force. But for a truss, we broke it out into tension and compression components in the top and bottom chord of our truss. Torsion, the one we don't really talk about very much, but it's the act of twisting, and it's kind of a funny combination of shear and moment, and we're not going to spend any time going over that in this course. Okay, let's do a quick refresher on our units. So we talked about how 225 pounds is 1 kilonewton. So for those of you that work in pounds, you can now kind of get a sense of what 1 kilonewton is. 1 kilonewton is 1,000 newtons. Earlier in the term, we were always working in kilonewtons and meters. A lot of what we do today, we're going to work in newtons and millimeters. So instead of kilonewtons and meters, we're going to be working in newtons and millimeters. So we're going to need to be able to convert back and forth. Luckily, we have the beautiful metric system where everything then is about multiplication or division of 1,000. 1 kPa was 1 kilonewton per meter squared. So basically, for every 1 meter by 1 meter area, we had 1 kilonewton of force acting on it. MPa is 1 newton per millimeter squared. So every 1 millimeter by 1 millimeter square has 1 newton on it. So that means MPa and kPa can be related. If we wanted to switch from MPa to kPa, we need to so 1 MPa, we are dividing by 1,000 to switch newtons to kilonewtons, but then multiplying by 1,000 and 1,000 to switch to meters squared. So 1 MPa is the same as 1,000 kPa. Strength. You guys remember, this is what we spent the first few lectures talking about. We want to make sure that the factored load is less than the reduced capacity. And we say less than, but that less than can be pretty darn close to exactly equal. So we'll often say equal is the same as less than. We'll often use these symbols to represent the fact that we factored the load or reduced the capacity. We haven't really looked at it much when we were factoring it. If you remember, I had that chart for you that showed what the different factors were. And in the building code, they used this symbol to talk about what the factors were. In this part of the course, or where we spend the time talking about the reduced capacity, this little symbol is going to be important to us. We're going to look for this symbol to see how much we reduce the capacity of different materials. When we were talking about the actual forces, we would use a little subscript F to remind ourselves that we were talking about a factored load. So if you came to me and said, here's the load, if it didn't have the subscript F, I would know I needed to factor it. If it had the little subscript F, I would know you've already factored it. And that happens a lot. A lot of times in offices, people will do one part of the problem or figure out the loads for the whole building and then pass it on to another person. So knowing if that little subscript F has already been applied is very important. The little subscript R means that the capacity has been reduced. And again, it's the same thing. Has that already been incorporated? Okay, here's where we start talking about the new part of the term. Stress and strain. So stress and strain are to the material what force and deflection are to an object. They are the effects on the material of an object subject to applied loads. What does that mean? If this was our object, we were applying a force to it. And now I want to talk about what happens to one tiny little block of it. So we applied a force, it deflected, so we had a force with a deflection, and now we're going to talk about what that means for stress and strain on this little cube of that object that has the force with a deflection on it. So it's easiest to work with axial forces, so we're going to start there. So stress versus force. So if we have an object with force on it, we are talking about one unit area of material with stress on it. So we were talking about objects. Now we're going to break it out and just talk about this little tiny block of the material. Basically, forget about the object as a whole. What does it do to the little tiny basic bit of element? So if there's force on the object, we're talking about the stress in the material. If we're talking about an object with deformation, forget that there is a force causing that deformation. We know there must be a force there, but that's kind of irrelevant to us at the moment. We have an object with deformation. We're talking about the strain on the material object. So if you hear deformation, think strain. If you hear force, think stress. Now you can see though that this deformation is caused by a force. So there's probably gonna be some way to equate those two things. And that's gonna come later in the term. Okay, let's talk about stress. Stress is defined as force per unit area. You're gonna see it's very similar to the load we applied to things because that was a force over an area. Remember when we were talking about KPA and we had 1 Arnold over 1 meter by 1 meter squared was 1 KPA, or we had a force divided by an area. Well, that was our overall object, and we talked about things a lot in KPA. We're now going to be talking about the unit material object, or a tiny little object. And so we're going to refer to it in newtons and millimeters squared. But we're still talking about a force and an area. So if we have that force over a particular area, we can determine the stress. So stress, and we want it to be in newtons and millimeters squared, or newtons per millimeter squared, or MPa. That means our force needs to be in newtons. Remember with Arnold, we had things in kilonewtons, or when we were talking about our force. So we would want that to be 1,000 newtons instead of 1 kilonewton. And our cross-sectional area, instead of 1 meter by 1 meter squared, we would be talking about 1,000 times 1,000 millimeters squared instead. So let's see what that looks like as an illustration. If we have this area with this force P on it, it is the same thing as that force spread evenly all over that area, or force divided by area. You know how I've often talked about, tried to describe my load as if I was spread evenly over the table. Well, what we were really talking about is a force spread over an area. So this is P divided by A. So this is our stress. Okay, so let's take that one and set it aside. Is there more or less or the same stress if we have the same force over a smaller area? Now, this is where I said in some ways you tend to think of things, people tend to get very nervous when we're talking about stress and strain, but you still do intuitively understand this thing. If you have your entire weight on both feet, so you have an area of both feet on the ground and your weight, you have a certain amount of stress you're exerting on the floor. What if you lifted 1 foot up? So you cut your area in half. Does the stress you exert now on that area below 1 foot, do you think that's more or less than the stress of both feet? Try it. Stand up. I'm going to try it myself. I'm going to stand up, and you can't see my feet, but I've got all of my load spread over 2 feet. When I lift 1 foot up, if I was standing on a mattress, for example, I would sink down just a little bit lower. Sink down. That sounds a bit like deformation and strain. But we just want to talk about force. But it's a good indication that I have more stress in that spot. So yes, for those of you who said there should be more stress here, let's take a look. We have the same force divided by half the area. Well, that's 2 times the stress, or we've doubled the stress. So again, just try to take a second and intuitively think about these things before you start your calculations. Okay, we have our force divided by our area, and we have stress. Is there more or less or the same stress if we have half the load on half the area? Well, if we only took half of our weight and put it on 1 foot, that should be fairly similar to our whole weight over on 2 different feet. So for those of you that think this is the same, let's take a look. We have half the force divided by half the area. The halves cancel out. We have the same stress. So this is why stress is really handy, because we can break it down into unit components so easily. We can talk about what's happening at the material level very easily. So these are equal to each other. So let's just take a quick look at an example. Okay, so here I am. I weigh 600 newtons, and I've measured the area of the bottom of my Blundstones, and they are 240 millimeters long by 75 millimeters wide. So almost 10 inches by about 3 inches wide. And I've got 2 feet. So that 600 newtons is, remember, stress is force divided by area. So my stress on the ground is, let's take a look at this. We are going to have 600 divided by 240 times 75 times 2. So we can see that plugged in there equals 0.0167 MPa. All right, so that gives us some information. We have zero clue kind of the scale of what that means yet. Loads, we kind of could get our head around just a little bit, but stress is less intuitive. This gives us a number, but it doesn't give us an intuitive feeling about any of this. Remember, newtons and kilonewtons, MPa and kPa are just basically different by 1,000 units. So let's see, if this was kPa, it'd be 1, 2, 3. I would be exerting 16.7 kPa of stress on the ground directly under my feet. Okay, all right. Now, if I went and put heels on, I'm feeling fancy, so I've taken off my Blundstones and I put on a pair of heels, do you intuitively think there is more or less stress exerted on the ground? Now, I'm going to assume that most of the load is on the front part of my heels. Now, for any of you who have ever worn heels, and it's, the picture time at a wedding and you're wearing your heels and you all go out and get the photographs, or maybe it was prom or some event where you're wearing heels, and you try to walk across grass, you try to stay on your toes because if you put your weight on your heel, you go right through the grass. That is because there's a lower area there and you're putting more stress on it, or the same force on a smaller area. So if I have just my weight on the toes of my heels, so just this part right here, let's take a look. Do you think there is more or less stress exerted on the ground? Well, we have 600 newtons. My weight hasn't changed, but I've got a smaller surface area now. So we've got 600 divided by 100 times 75 times 2. We're going to get 0.04 MPa of stress. So a higher stress. And that makes sense. We've got a smaller surface area, but the same load. Now, I go and grab my snowshoes instead of my Blundstones or my heels. I've got 600 newtons, the same load, that hasn't changed, over a much larger surface area. So my snowshoes are 1 meter by 150 millimeters wide. So now I've got, and intuitively, what do you think? More or less stress. And probably intuitively you understand that there should be much less surface stress between my feet and the ground now. And that's exactly why we use snowshoes, is because snow can handle a much lower stress. You're already getting the concept, looking at this, of what we're trying to do with our materials. Our applied load has to be less than the capacity. And snow has a lower capacity than, say, dirt to hold that load. So 600 divided by 1,000 times 2 times 150 equals 0.02 MPa, so a much lower stress. Now, remember how I talked about factoring and reducing the capacity? So say you had snowshoes that were, or you had snow that had exactly 0.02 MPa of capacity. If you changed your weight around or you lifted 1 foot off the ground, your snowshoes would go down in the snow. And that's why we try to build in a little bit of a buffer. We factor up our load and we reduce our capacity, and then try to find the right snowshoes, for example. All right, let's do another example. So what is the stress if what is the stress an elephant exerts on a floor if it weighs 44 newtons and its feet are approximately 500 millimeters in diameter? I don't think I'm going to put the calculation sheet down for this. I think this one's pretty easy. We can talk it through. Well, we know that we want to switch those kilonewtons into newtons. When we're talking about stress, we want to be in newtons and millimeters. So 44 times 1,000 equals 44,000 newtons. Okay? Area, we have 4 feet of our elephant. Its feet are approximately half a meter around in diameter, or 4 feet times pi r squared. And our r is 500 divided by 2. Remember, r is radius, which is half of the diameter. So 4 times 3.14 times 500 divided by 2 squared. We're going to get 785,398 millimeters squared. So we have a force and we have an area in newtons and millimeters squared. We can calculate the stress the elephant exerts on the floor. So 44,000 newtons divided by 785,398 millimeters squared, and we get 0.056 MPa. Me in heels was 0.04 MPa. So I exert the same stress as an elephant? That seems kind of insulting to me. But this is why understanding what the area is very important. You want to be talking about the same thing here to understand what stress means. What if the elephant snuck in to my closet and stole 2 pairs of heels? So instead of being its load on 500 millimeters in diameter on all 4 feet, tried to jam each foot into my heels. So that sneaky elephant is now wearing my best pair of heels and my second best pair of heels. Let's see what that is. So it's got 4 feet, and we had 150 times, what was my feet? 100 times 7, so no, sorry, my heels were 100 by 75, so we have 100 times 75 times 4 feet, so we have 30,000 millimeters. 44,000, which is our newtons, divided by 30,000 millimeters, we're going to get, that's really bright, sorry guys, we're going to get 1.46667 MPa. So if that elephant was also wearing my heels over those 4 feet, its stress is so much higher on the ground. So it's all about that force and that area that is defining what that stress is. That's why stress is so handy, that we can talk about just the little kind of unit element below our foot, whether it's an elephant without heels or Shannon in heels. The fact that we're exerting pretty close to the same stress on the ground is what we care about. Well, let's relate this to maybe something that's slightly more handy for talking about buildings. What if I said steel can support around 350 MPa of stress? You don't know where that came from. You don't know what that means. But if I said that snow can exert 0.01 MPa of stress, and that's why we needed the snowshoes, you kind of get what I'm talking about. So I'm just flat out telling you we're talking about a material that happens to be steel that can support 350 MPa of stress. It has the ability to not fail if it's supporting anything up to 350 MPa of stress. Over that, it's ruined. We don't know what that means, where it came from, but I'm telling you that this is the material that we're talking about right now. And we have a 1 inch by 1 inch cube of it. So we have 25 by 25 millimeters of steel. I am going to add that. I'm going to add the fact that it's supposed to be millimeters into that slide. Slide 18. I'm going to add in the millimeters into that note, just so you guys are really seeing that we're talking about 25 millimeters by 25 millimeter cube. Okay, we want to know what force it can take, though. We've been told what the stress capacity is. It's 350 MPa. Area, no problem. We can figure that out. It's 25 by 25 millimeters, or 625 millimeters squared. We know that stress equals force divided by area. Now it's a simple matter of rearranging this. We can take our stress and divide it by area to figure out what force that can take. So 350 divided by 625 millimeters squared gives us 218,750 newtons. Well, great. We were dealing with stress, so we wanted everything in newtons and millimeters. But once we're talking about force again, we're kind of lazy and we like to talk about things in kilonewtons. So now we're going to switch it back to kilonewtons. I know, it is so hard to multiply and divide by 1,000, but that's exactly what we're going to do. We're going to divide this by 1,000 now to talk about it in kilonewtons, and we can see that we have 218.7 kilonewtons. So a 1 inch by 1 inch cube of steel can support 218.7 kilonewtons, assuming it can take 350 MPa of stress. I want you guys to pay attention to units when you're looking at your assignment and the quiz. I will always tell you what units I want your answer in, but I might not give you the units that you need to to find that answer. And you might have to switch between kilonewtons and newtons and millimeters and meters to make sure you're working in the right units. Be very diligent about the units. Okay, let's talk about strain. I find intuitively people really struggle with this concept of strain, because when we're talking about strain, I'm telling you to forget about what the force is. No one cares. We're not talking about the force. We just want to know what the effect the force has on the object. And so people struggle with that. How can that be independent of the force? Well, in some ways, it's not independent of the force. But talking about the strain on its own is independent of the force. So strain is the relative axial deformation of an element subject to an axial load. An axial load that we don't care what the value is, but we want to know how much our object has deformed. So we have an original object dimension. So we have an object like this, and we're applying a load. So you can see that those little cubes are deforming. So we have how much that object is originally, and we care how much it's changed. So strain is a dimension divided by a dimension. It's unitless, which really messes with people's heads. I find it's often handy when I'm talking about strain to just remind myself where I'm coming from. Even though it's unitless, it's millimeters divided by millimeters, I'll often find it handy to kind of just keep track of my units off to the side, and I'll write millimeters divided by millimeters just so I don't lose track of things. It can be very handy. So we also want to know what the change in length is. So that is the length after the load's been applied minus the original length. And that is our axial deformation. So this is how much has it changed? We have the final length minus the original length. Or really, it's the final length minus the original length divided by the original length. Let's take a look at this as an illustration. I find that a little bit easier to talk about. So we have an object with some length, and there's a load applied to it. We don't care what the value of the load is, but we measure that the object changed this much. So this is our final length, meaning that this is our change in length. Strain is our change in length divided by the original length. Let's take a look at another one. We have something that is half the length with some load applied to it. We don't care what the value of that load is. And it changes the same amount. So we have the same amount of deformation, but only half the original length. Do you think there is more or less strain on this object? So we had a smaller original length, but the same amount of deformation. Let's take a look. Original length divided by half the original length. So we have the change in length, which is the same as our first example, but only half the original length. We have 2e. So there's twice the amount of strain in this. Let's look at another one. We have half the original length, but only half of the amount of deformation. So half of the change in length, but we have half of the original length. We're going to have the same amount of strain. Let's look at an example. Okay. Here's Dave. Say hi, Dave.
Okay.
This is much more fun for me now that he's sitting beside me. Usually this was done and people hadn't met him yet. Here's Dave one time with a fantastic mustache. And it was in the summer. And Dave was fit. Dave was in great shape. He had been working out. He had been lifting lots of heavy things outside. And he puts on his shorts, and the elastic fits perfectly around his waist. It's exactly the right fit. He needs absolutely nothing to hold those shorts up. So his shorts are the exact perfect fit. But fall comes along. There's lots of events, Halloween candy, so much Halloween candy. That reminds me, I'm going to take a drink of my coffee. And those shorts are starting to get a little bit snug. So he pulls his shorts up, and that elastic is stretching just a little bit. So there's a little bit of stretch in that elastic around his shorts. And then January. Whew, after the holidays, lots of beer, lots of turkey, lots of eggnog, lots of chocolate. And Dave goes to put on those same shorts, and man oh man, is he ever stretching or straining the elastic on those shorts. So this is where intuitively I think you understand. For all of these examples, when he's got the shorts in his hands just before he puts them on, they all have an original length. The original length is the exact same no matter what. That's the elastic band in his shorts. In the summer, when he puts those shorts on, there is no change. There is no delta. So there is no strain at all. There is zero strain on that elastic. In the fall, there's some delta or some stretch or some change in length, even though they all have the same original length. So there's some strain here. In the winter, there is lots of stretch in that elastic or lots of delta. So there's lots of strain in that elastic. So intuitively, I think now you kind of understand what we're talking about. We're going to bring it back to objects that maybe are a little bit harder to talk about. So, I'm trying to decide if I want to turn the page down for you guys. Okay, these are still pretty easy examples. I don't think I need to work out the calculations by hand. So, we have an object that is 25 millimeters tall. So we're talking about 1 inch tall. Remember how in the other one we had a surface area that was 25 by 25? Well, now I'm talking about one that is 25 millimeters tall. And we've been told it deforms 1 millimeter. We don't know what load was put on it. We don't know what happened to do this, but we know that it was 25 millimeters tall and now it's changed by 1 millimeter. Now, some of you are asking, did it stretch or did it compress? Answer is, I don't know. They've just told us that it's 1 millimeter. I don't know what's happened there. They didn't give us that information. They've only told us that it deforms 1 millimeter. So we have 25 millimeters of original length, and we have a change in length of 1 millimeter. So what's the strain? Strain is change in length divided by original length, and we have 1 millimeter divided by 25 millimeters, or 0.04. Unitless strain. Now, sometimes I'll write millimeters divided by millimeters just to kind of help myself keep track of that. So why do we use the original length when we're talking about strain? Why don't we use the final length? Well, there's two reasons. For one reason, it's that the difference is very, very tiny. But the other one is it makes it easier to not worry about whether it is stretching or compressing. All of a sudden, if it's stretching or compressing, becomes really, really important. So let's take a look at an example if we used the original length, which is what we do, and the delta, or if we used the final length and we knew it had stretched a millimeter, or if we used the final length and it had compressed a millimeter. So this is what we do. This is the way we do it. We have 25 millimeters. We know that the change in length is 1 millimeter, and we calculate our strain. If in that calculation we didn't use final length, but we didn't use final length but original length, and it had stretched a millimeter, we would have 1 millimeter divided by 26 millimeters, or 0.03846. So pretty darn close to the same answer, but it is less than that. If it compressed 1 millimeter, our final length would be 24 millimeters, or 1 millimeter divided by 24 millimeters. So all of a sudden, knowing if it was tension or compression becomes really important. So the kind of standard that we use is we make use of the original length. All right, you understand all of this. You know what stress is, you know what strain is. Why do we care about this unit element? Why don't we just talk about it in force and deflection? Why the heck would we bother with this at a material level? Well, if we want to measure deformation of things and we are applying these loads to a building, it's pretty frackin' hard to measure those deformations. So if this is our unloaded building and this is our loaded building and it's deformed, you probably would need a surveyor to measure that deformation. Some things it's a little bit easier. A cable with a high load, you could probably maybe visually see it, but even then it's still pretty hard. We need a way to be able to talk about these things or do all of the tests to figure out how these things behave in a lab. We need to know how to figure this out in a lab and then extrapolate and apply it to a building as a whole. And that's why talking about things in stress and strain is so important, because now we can talk about things at a material level and then extrapolate it to the building as a whole. So the part behaves like the whole. It's really hard to test full-scale elements. Knowing the part of it behaves like the whole of it, we only need to test these little tiny little bits of it to understand the material. So often, for example, if it was steel, we'd test a coupon or a dog bone sample. So if it was an axial load, we'd stretch this, we'd measure the deformation, and we'd measure when it failed. Then we could calculate what the stress and strain are, and then extrapolate that and apply it to whatever members we actually have. So, what are the exceptions to this rule? So these make sense most of the time. When do these rules stop making sense? Well, when we have phase changes, when we go directly from a solid to a gas or even some stage in between. So let's say an ice hotel evaporates, for example. That's sublimation. The normal rules are not applying in that example. Extreme temperatures. Steel in a fire, for example, and steel is very susceptible to high heat. The normal rules we're about to start to talk about for steel don't apply. It is experiencing a different, the rules are changing for how steel behaves under very high heat, which is actually how, unfortunately, some of the things, one of the problems that was within the collapse of the Twin Towers was that jet fuel burnt so hot that it actually weakened the steel, because the Twin Towers were designed for a plane to crash into them. That part was built into the design, and we saw that they didn't collapse due to the impact, that resounding impact of a plane hitting it. Yes, there was already loss of life and already extreme damage, but it was localized. The building didn't collapse due to that impact. It was a few other things that caused that, one of them being the intensity of the fire that resulted from the jet fuel. Extreme stresses and strains. For example, you wouldn't expect your building to behave the same in a black hole. I know, I'm being a little bit ridiculous there, but extreme stresses and strains. So you could be talking about things like maybe within a volcano or kind of the creation of diamonds, for example. There are changes to stress and strain there. We're talking about realignment of particles. Our rules that we're talking about for stress and strain wouldn't apply. Okay, here's where it gets really, really cool. There is a relationship between stress and strain. Modulus of elasticity is the measurement of the stiffness of a material and is divided by stress, is defined as stress divided by strain. So E, the modulus of elasticity, or Young's modulus, depending on what material you're talking about, is stress divided by strain. And we like to look at this. This is talking about the linear relationship between stress and strain on a particular part or in a particular zone of a material's behavior. And I'm going to show you what that looks like. So this is something we can use in the zone we like to work with materials in. I said that there are kind of changes that can happen in a material. Well, we only talk about a very small range of material behavior for certain materials. So let's take a look. If we know that E, which is just something we're creating, E, the modulus of elasticity, we just want to relate stress and strain. So we have the stress divided by the strain. But if we know that stress is force divided by area and strain is delta L divided by L, and we're just saying E is this measurement or this value stress divided by strain, we can figure out a bunch of things. E then would be stress divided by strain, or we can rework this and kind of clean it up a little bit. E is force times length divided by change in length times area. So all of a sudden, we have our force, we have our length, we have our change in length, and we have our area. So now all of a sudden there's this relationship between that kind of unknown what was causing that deformation for strain related to our stress. And that relationship is E, or our modulus of elasticity. And we're going to see what that looks like. We're going to plot some of those out in just a minute. Okay, so if we know length and area, we can now calculate the force or the deformation. And for common building materials, we know the stresses and strains in their normal areas. We can take those coupons or dog bones of materials, or we can take cylinders, or we can take a cube of element of the material and test it again and again and again and figure out what the stresses are that it fails at or the strains that it fails at, which means we know what the stresses and strains are in their normal range. If we know what member we have, we would be figuring out what length we're using, we know what load is being applied, or we know the cross-sectional area of the material as a whole. We can now maybe figure out some things about our material or our member. So if we know what the modulus of elasticity of our material is, and remember, modulus of elasticity can be figured out by testing small elements to figure out what the stress and strain is on a material element, which means we can figure out how a material behaves. So we have E. If we know how much deformation we're going to get, and we know what our cross-sectional area is, and we know what our length is, we could figure out what force is on this object. Now, this all still seems like a bit of a stretch, I think, until I show you this relationship E. But we're going to start with a few quick examples, and then we'll look at that relationship between those two things. I'll show you how it all ties in together. I said that we like talking about things in stress and strain because we can test it at a unit element. Remember, stress divided by strain is MPa divided by a unitless element. So our E, or our modulus of elasticity, is also in MPa. People have, over the years, tested lots of elements, and we know what their modulus of elasticity is. Structural steel, 200,000 MPa. That's the only one that I want you to memorize. You should know that steel has a modulus of elasticity of 200,000 MPa. What I would do if we were all in person is I would make you all say it aloud together. And in fact, I would randomly, for the rest of the term, just stop and say, what's the modulus of elasticity of steel? And I would expect everyone to go 200,000 MPa. I can guarantee you, you need to know this. But I've told you you need to know it. Here it is. Steel, E equals 200,000 MPa. What are some of the other ones? Well, stainless steel, which I know you're thinking, Shannon, that's steel. But it is steel that has a different alloy to it. It is a slightly different makeup of steel. So it is a specific thing. 180,000 MPa, so it's not as stiff. Aluminum, 69,000 MPa. A lot of times, especially because my firm is designing small scale elements, people will come to me and say, instead of steel, could we use aluminum because it's so much lighter? It's about half the weight. Is that going to solve our problems? Could we just make it lighter with aluminum? But I have to point out that it is about a third the stiffness. So all of a sudden there's much more deformation. And we're going to see that deformation, when you're talking about certain materials, can be what ends up governing the design. So going to a lighter material doesn't always help us solve our problems. Concrete, 17,000 MPa. Now, there's some caveats with concrete because this is compressive. We only care about concrete in compression. In tension, it doesn't have any strength, so we're not even going to worry about it. Wood, pine, for example, is 9,000 MPa. So it's about a 20th of the modulus of elasticity of steel. Again, this doesn't mean much to you guys. What can we do with these things, Shannon? Well, let's start looking at some examples. Let's take a look at our steel cube. It's 1 millimeter by 1 millimeter by 1 millimeter. That's a really good size object to talk about. I use 25 millimeters because that's about an inch. And all the old school people, the old people, oh look, he knew right away, will talk about it in inches and pounds and pound force. We're going to be working in everything in metric. So we're going to use a 25 millimeter by 25 millimeter by 25 millimeter cube. And we've been told that this deforms 1 millimeter. What was the force on that cube? So we know its original length was 25 millimeters. We don't care whether it was compression or tension. It's deforming 1 millimeter. So we know our change in length. We know our surface area was 25 millimeters by 25 millimeters. So 625 millimeters squared. And we know E because it's steel. Somebody has tested this again and again and again and again and seen the relationship between stress and strain and told it to us is 200,000 MPa. The only thing we don't know is what the force was. Well, we know, so we have the original length was 25 millimeters. The change in length was 1 millimeter. The area is 25 by 25 or 625 millimeters squared. And we know the E for steel is 200,000 MPa. Well, the force, E equals force times original length divided by, oh, look at that. I've got an error in that slide too. Slide 34. We're missing the delta L. That should be delta L times the area, or 200,000 equals P times 25, or original length, divided by our change in length times our area. We could rearrange this first. Remember I showed you those equations where we could actually rearrange this? I just wanted to show you that you could rearrange it with the numbers or after the numbers have been inserted. It doesn't matter what way you like to do it. Our force is 5 million newtons? What the heck? That is huge. This is why once we're talking about the force, we like to switch it back into kilonewtons. I know, it's a pain in the butt that when we're talking about stress and strain, we work with MPa or newtons and millimeters. And then once we're talking about the final thing, we're working in kilonewtons and meters. So we're going to switch this into kilonewtons because if we're talking about force, we like to talk about it in kilonewtons, or it's a slightly more reasonable number of 5,000 kilonewtons. But that's still 5,000 Arnolds. So we have this object that has 5,000 kilonewtons on it, causing that 1 millimeter of deformation. Now, how many kilonewtons did we say that 1 meter by 1 meter cube of steel could take? Yeah, it was only 218 kilonewtons, I think. So it looks like this would actually fail that object. It doesn't seem like if we knew how much stress a steel object could actually take, that this could even be possible. But that seems a bit beyond what we're talking about right now. We don't really know where that comes from, but I'm telling you that this couldn't work because we already did a calculation that if steel can only take 350 MPa, we couldn't get this much deformation. So that's around 5,000 Arnolds or 114 elephants. Yeah, so 114 elephants stacked on top of each other would move a steel cube 1 millimeter. All right. What if we had rubber, which has an E of 55 MPa? And I can tell you everything that I've talked about in this lecture, I've actually looked up. An average weight of an elephant is around 44 kilonewtons. The diameter of an elephant's foot is around half a meter. The E of rubber is, if you're talking about particular rubbers, is around 55 MPa. So how much load does it take to deform a 25 millimeter cube? So the same 1 millimeter or 25 millimeter by 25 millimeter by 25 millimeter cube. Do you think it's going to take more or less force to deform this cube the same amount? Just intuitively think about it. If you took a cube of steel and a cube of your eraser and squished it, do you think you'd see the deformation in the steel? No. Would you see the deformation in the eraser? Probably, yeah. So it seems like it should take much less force to deform that same cube 1 millimeter if it has a lower modulus of elasticity. So let's take a look. We know that it is 25 millimeters long. That's its original length. Its change in length is 1 millimeter. That hasn't changed. We know its area is 625 millimeters squared. That's the same. The only thing that's different is the stiffness of the material, or the modulus of elasticity, or the E of the material. And this has come from all kinds of tests that they've been able to tell us, yeah, the value of that is 55 MPa. Let's do the exact same calculation we did before. So here I've actually rearranged the equation first. P is E times the change in length times the area divided by the original length. We get 1,375 newtons. That's a pain in the butt. We like to talk about it in kilonewtons, or 1.375 kilonewtons. That's around 309 pounds. So it takes much less force to deform that piece of rubber, that same size piece of rubber, than it does to deform the steel object. All right. Let's look at the stress-strain curve of these objects. So stress-strain curves describe the behavior of a material under a wide range of stresses. So essentially what someone has done is for all the different materials, or a lot of different materials, they have said, okay, I've got this little object and I'm going to put a very little amount of force on it. How much did it deform? I'm going to put a bit more force on it. How much did it deform? I'm going to put more force on it. How much did it deform? And they kept doing that all the way up until the object failed completely. They destroyed the object. And then they plotted those points relative to each other. They put the strain on the bottom and the stress upwards. So the strain is our horizontal axis and our stress is our vertical axis. And they've plotted all of those out. Well, E is the relationship between those two things, the force divided by the strain, or the stress divided by the strain, is E. So we are plotting the E of the object. We care about E when it's in this nice, beautiful, flat, even part of the stress strain curve. And we're going to see what I mean by that in a minute. So before we talk about that, let's talk about some useful terms engineers should know. And some of them that you should too, because they're pretty handy. Most of them are ones you kind of know and you use all the time. And really, this is where they're coming from. So elasticity. That's the tendency of a material when unloaded to revert to its original shape in the opposite manner to which it became deformed. Literally, an elastic. So if I put a force on this object and I strain it, there is some deformation. When I let go, it goes back to its original shape. There is no permanent deformation in that elastic. I've strained it, and it goes back to its original shape. There is no permanent deformation. Plasticity. The deformation of a material undergoing non-reversible changes of shape in response to applied loads. This one's a little bit harder to talk about. But if you can, go find a paperclip. Pause me and go find a paperclip. Paperclip is a really good object to try to demonstrate elasticity and plasticity. So if I have a paperclip, this is in its original shape. If I put a few pieces of paper in here, I've deformed it. When I let go, it goes back to its original shape. If I put too much paper in here, so I've got lots of stuff in here, I've got lots of deformation. Look at how much strain there is in this. When I let go, it reverted some. Like look, it sprung back a tiny bit, but it didn't go back to its original shape. That is permanent or non-reversible changes in shape in response to the applied load. But you saw that there was some amount that it did spring back. So there was some elastic component and some plastic component to applying that amount of load to our paperclip. Yield stress, the point at which a material transitions from elastic behavior to plastic behavior. At this point, some portion of the deformation will be permanent. Now, this only applies to plastic materials. Some materials have no plasticity whatsoever. Wood, zero plasticity. We are elastic, so you can load it and unload it. It goes back to its original shape. But when you get to the limit where it reaches the maximum point, it fails. There is no zone where you can deform it and it springs back. Or sorry, that it doesn't spring back. It will always spring back or it will fail. Concrete, same thing. There is an elastic zone in concrete where you can apply load to concrete and it deforms, and when you unload it, it springs back. But after you apply too much load, it has permanent deformation. It doesn't undergo permanent deformation. It will fail completely. Steel has this beautiful plastic zone. I can stretch it, and it springs back, and then I've got permanent deformation. That is a plastic material. Or it's got ductility. Ductility is a really fun way or nice way to talk about it. Ductile, a material which will undergo large permanent deformations, thereby absorbing a great deal of energy before failure, is a ductile material. A material which has no ductility is brittle, or a material that has no plasticity is brittle. So we could say that our concrete and our wood are brittle material. Our steel is a ductile material. So it can, one of the great things about that is it can absorb large amounts of energy. which can be really useful for a few things. It can be helpful for our seismic. But another thing is that the large permanent deformations give us a really great indication long before failure occurs. So with wood and concrete, we don't know we have a problem until we have a problem. With steel, if we see large scale deformations, we have a good indication that we're approaching failure, and maybe we have time to do something about an imminent failure. So brittle, a material with no plastic zone. Ultimate stress, the maximum stress that a material can sustain. For brittle materials, that is at the end of the elastic zone. For ductile materials, that is at the end of the plastic zone. So I've told you all of these terms without a visual graphic to look at. Now we're going to look at the visual graphic and we can see what I'm talking about. So the stress strain curve of concrete. What was one of the things I said about concrete? I said that it is a brittle material. It has no plastic zone. We have a linear relationship between stress and strain, or the elastic zone, until it fails. So if you test concrete, when there's a little bit of strain on it, there's a little bit of load on it. When there's a bit more load on it, there's a bit more strain. And we go along until it fails. And then it's done. We have nothing else. At any point along here, if you unloaded the object, it would go back to its original shape. We can plot that relationship between stress and strain, and that is our modulus of elasticity. In this case, this particular example, E was 32,000 MPa. I showed you a chart that had a particular E for concrete. Concrete, its modulus of elasticity is dependent on quite a few things, and we make every batch of concrete. So E is basically, we have to determine E each time we make concrete. So we have a range of E for concrete. This is the ultimate stress. So we've gone through and we've loaded it until it failed. And as we loaded it, it deformed until it stopped deforming and it failed. So this is the stress strain curve of concrete. I say idealized because it's not quite so smooth, it's not quite so perfect, but for the most part, this is how engineers treat the stress strain curve for concrete. Look at this. Anywhere in this zone, if we unloaded it, it would spring back to its original shape. It has an elastic zone. It does not have a zone where it has plastic behavior, where we'd unload it and it would revert somewhat, but not completely back to its original shape. It has no plastic zone and it is brittle. We do not like brittle things. What could we do to concrete to make it less brittle? Or what could we do to help us out with that? I wonder if we put something in it, say steel, to make it slightly less brittle. Yeah, that's probably a cool thing to think about. We should talk about that later in the term. All right, let's look at the partial stress strain curve of steel. So steel is the exciting stress strain curve because this really kind of demonstrates all of these things I've been talking about so far in this lecture. The stress strain curve for steel has a huge range in it, and we only care about a wee little tiny portion of it. So I'm going to zoom in on a tiny portion of the stress strain curve of steel right now. The next slide, we're going to go a little bit further. So look at this. We have our stress. We have our strain. Somebody has plotted excuse me, sorry folks. Somebody has plotted, has tested a little sample, and they've plotted as they increase the stress, they've measured the deformation of it. This is our nice flat slope, or our E, or our force divided by our area, or our stress divided by our strain. or sorry, not our force divided by our area, sorry, our stress divided by our strain is E, and it's been plotted as 200,000 MPa. So this is our slope of our line here. This is when it starts to transition, or this is when it starts to transition from a nice elastic zone to a plastic zone, or we call that yielding. Yielding is when we transition from a plastic to, or an elastic to a plastic zone. So if we know what value that is, we know what stress we transition from elastic to plastic. That is when we start to yield. I'm just going to go back to that concrete one for a second. This point here was our ultimate stress. We can figure out the maximum stress this object can take. We know above this stress, and our concrete failed because it tried to go into a plastic zone that didn't exist, or it was brittle. So we know, I hear little footsteps up there, Dave. Someone's out. 6:30 and they're awake. Damn it. So we know the ultimate stress of our concrete. If we knew that concrete failed at some value, we could start to figure stuff out. Remember, reduced capacity, greater than factored load. Okay, so for our steel though, we have this value called the yield stress, where we transition from elastic to plastic behavior. In steel specifically, we call that Fy. Why do we call it Fy? Because it's really annoying trying to switch to Greek letters on a keyboard. When you're writing it out by hand, no big deal. But when you're typing it, it's a pain in the butt. I can tell you from making all of the lecture slides, all of the PDFs, all of the kind of assignments in Quercus, trying to switch one letter to a Greek value is a pain in the butt. In fact, one year, the exam, I created and sent it to the department. This is when we did exams in person, and they didn't realize the importance of it. And without telling me, they said they had a standard font for everything. So they just took my entire Word document and changed it to a particular font and undid all of the Greek letters in the entire exam. You can imagine how much I cried when we got into that exam at that set time slot, and none of the Greek letters were there. Nothing was right. It was a very stressful exam, you can imagine. So that's why for steel, for example, we'll call that yield stress Fy. So if we know what the yield stress is of steel, because we test it again and again and again, maybe we can do something handy with that. That's the proportional limit. After that, we're starting to do some weird things to our steel. So let's talk about this. In this zone, it's elastic. In this zone, it's plastic. Anywhere in here, if we apply a load to it, we'll experience a strain. But if we take the load off, we'll go back to zero strain because there's no permanent deformation. In the plastic zone, if we apply a load, we have a strain. When we unload it, it will revert back some, but not all the way. There will be permanent deformation in this material. Let's take a look at it. Let's take a look at loading and unloading in an elastic zone. We load our object to this value of stress and this value of strain. When we unload it, there is no permanent deformation. If we load it into the plastic zone, we go all the way up into the plastic zone. When we unload it, there is permanent deformation. So look at this. We unload it following that same modulus of elasticity line. So we have some residual strain. There is some permanent deformation. So we loaded it. We loaded our paper clip some amount. We've loaded it quite a bit. When I let go, it deforms. It goes back some, but there is some permanent deformation within that paper clip. That permanent deformation is the residual strain, or the deformation that's left even though there's no load applied anymore because we've taken all the load off, but there is some permanent deformation. We can do it again and again and again. And each time we can get more, if we go back up to that amount of load that was applied, we can get more residual strain. Or we could just go up and load again and come back down to just that same residual strain. Okay, let's look at the entirety of the stress strain curve for steel. I'm going to tell you, this makes a fantastic exam question. Maybe say if someone printed off the entirety of this and highlighted a few key components of the stress strain curve and said, hey, what are each of these components? And you had to label it. That seems like a lovely, lovely exam question. Maybe one worth like 5 points, say. All right, here is our elastic and just transitioning into the plastic zone. So this was the part of the slide we just looked at. You can see it's just a tiny little part of the stress strain curve of steel. This is the entire curve for steel. There is weird stuff happening here. We're not going to worry about it too much. I want you to recognize that this is what the stress strain curve of steel looks like. This is where it yields. So this is what we care about, is right here, where a modulus of elasticity is this line, or the relationship between stress and strain in the elastic zone. This is where our steel starts to yield, or where it transitions from elastic to plastic, or where we transition from non-permanent deformation to permanent deformation. This is the maximum amount of load our steel can take. So it can take more than the yielding value. So this is where I said steel can be really handy because it starts to yield and we get permanent deformation, large permanent deformations. You can see here, we're increasing the force with very little strain increase. Here, with lots of force, little strain. Here, little force, lots of strain, meaning lots of permanent deformation. If we see lots of deformation in our steel, we still haven't failed the member, which means we've bought some time to maybe evacuate a building or do something else with that time. And so here's then the permanent or the ultimate stress of our steel. Here is the strain at rupture, where there's a large amount of deformation. But look at, here was the strain at yield, and here is the strain at failure. So we had very little deformation in this zone. And this is where I often suggest to people, you can take your paper clip, and we had a little bit of force where we had yielding. So there was some force at yielding, but if you wanted to take it and figure out what rupture was, there was a large amount of deformation in there. If you touch it, if you did that, say, if you did this and worked your paper clip back and forth a bunch, so you kind of did permanent deformation and then put it back again and again and again, you would start to feel that the steel gets a little bit warm. It's because there's lots of energy that goes into that ductility of steel. If we loaded this object up to this point, if we unloaded it, we know that there is some amount of permanent deformation. We'll unload it following the line of the modulus of elasticity, and this is all residual strain. So yeah, if we loaded a building up and we saw huge amounts of deformation and we saw that the thing might start to fail, so maybe there's a 1 in 200 year snow event or a hurricane, we get large permanent deformations, but our building hasn't collapsed. When the hurricane stops or the snow melts, yeah, there's going to be lots of permanent deformation, but we didn't have failure. That was the plastic strain energy. What if, say, there was an earthquake? Well, earthquake puts a lot of force into something. What if we allowed it to be ductile so it could absorb a lot of energy? What if we used that to our advantage? I've said before that there's not much new. Everything that we're doing in these lectures was figured out, 120 years ago. There's nothing new we're talking about. These are all old concepts. Nothing has changed. Very little in the field of engineering is new. Now, I say that kind of flippantly, just the stuff we're talking about, very little is new. But remember I said earthquake design was kind of a hard one to talk to you about? That's because we have figured out that if we allow large-scale deformation, we can absorb a lot of energy in the building. And maybe it actually lowers the forces that our building sees. So if we, instead of designing for a huge force, allow deformation and allow energy to be absorbed locally, we can limit the force that the rest of the building sees. And that is called ductile design, or basically it is a method of design that was implemented in around 2004 in the building code. Very rarely needs to be used in Toronto, very important in Ottawa and Vancouver and California, for example, where we see earthquake design. So we're not going to touch on that, don't worry about that, but I want you to understand that capacity design or ductile design is using that idea that energy gets absorbed in large-scale deformation, and it really has a big impact in earthquake design. So this was our plastic strain energy. That's how much energy was used to permanently deform the object. This was our elastic strain energy, or how much energy went in to deforming it the amount that it could spring back. Or when it was loaded, this amount was our potential energy to spring back. This amount was fully absorbed into the object. The modulus of toughness is the area under the curve at the point of rupture. So this is how much basically energy it took to fully fail that object, or that's how tough the object was. Okay, what are some common yield stresses and ultimate stresses of objects? Well, structural steel has 300 or 350 MPa of yield stress. Remember I told you that it had 200,000 MPa for E? Well, we now know its yield stress and we know its ultimate stress. Stainless steel, 250 MPa and 505 MPa for yield and ultimate stresses. I've already told you what its modulus of elasticity is. Look at this. Brass, concrete, wood, no yield stress because they are brittle materials. There is no plastic zone for those. Remember, yield stress talks about the transition from elastic to plastic. Ultimate is the stress that it finally fails at. Well, these never switch from elastic to plastic. They stay in the elastic zone until they fail at the ultimate stress. So these would be the worst stresses we would allow our material to see without failing. So under this, our object doesn't fail. We like to keep our objects that have yield stresses in the yielding zone quite often because we don't like permanent deformation. Sometimes we like permanent deformation because it tells us when we have a problem, but we certainly don't want everyday objects to be allowed to experience permanent deformation kind of in the everyday running of a building. So we keep our yield stress as the maximum stresses we would let our objects see, and for brittle materials, it's the ultimate stress. I'm going to, at this point, get you guys to watch a video. I'm trying to decide if we should watch it together. It's a little bit annoying because there's a funny lag in sound. I can't really talk while we're watching the video. But this was a great YouTube video produced by a lab in the UK that shows two different materials with their coupon being tested to failure. And you can see within that where it transitions from yielding to where it goes from the elastic zone to the plastic zone and then ultimately to failure. They do two different ones. You can see our steel, which is the one that we've talked about, and they do an aluminum alloy as well. If I'll put the link to this video in the lecture slide. So I suggest you watch it. One thing it's nice is that they say all the same things I say, except I think they make it more complicated when they talk about it. Sometimes it's nice to hear it in another voice, but it's also good to see that I'm not just making these things up. They're all standards that get talked about again and again. They plot, instead of stress, well, they've plotted this in the opposite direction. Don't worry, no, they've labeled this wrong. That should be strain and that should be stress, because it's newtons per millimeter squared. That's a flaw I've never noticed on this before. I'm going to overwrite that in the slide as well. Slide 44. In the video, they plot it as force versus deformation. But remember, they know their object. They know the original length. So if they're plotting deformation versus load, they know the area of the object they're testing and they know the original length, which means they can very easily, and those don't change as they increase the load and the deformation increases. They can easily convert that. That graph would look the exact same if they plotted it as stress versus strain. The nice thing about plotting it as stress versus strain is then you can go to a different object and that plot should look the same. So take a minute and watch this video. Okay, we are not going to spend much time talking about shear stress and strain. I just want you to know it exists. And really, remember I said that stress is taking these two planes and shifting them relative to each other. Well, look how this object moves. Oh, hi, buddy. You want to come give me a quick morning hug? Do you want to say hi to all my class?
Hi.
Be quiet. I think your brother is still asleep. Is he awake or asleep?
Awake.
He's awake. Oh, good. You're both awake. Okay, you go in the other room. Let me say hi to... Hi, Duncan. Can I have a hug?
I love that.
I'm not all done. I just need a little bit. Sit. Oh no! Look at the camera. Look at this way. Say hi, everyone.
Hi, everyone. Anybody right there?
I know, but they're gonna watch it. You know how you watch videos on your tablet sometimes?
Yeah.
They're gonna watch this video like that. They're gonna watch us the way you watch your videos.
How?
Isn't that cool? Okay, listen, you're the cutest.
Come on, Doug.
You go in the other room now. Okay.
Come on, Dougie.
All right. Someone last year complained that it was unprofessional that my kids showed up in the video. I personally think that COVID, man, that's our life. We're trying to work from home, teach from home. You're trying to watch these from home. I'm sure at least one of you has had your cat walk across your computer at this point. So let's try to withhold judgment. And later, some of you might already be parents. I don't get to see you guys. I don't get to talk to you. Some of you are nodding your head and understanding it all right now. Some of you may choose to understand that later in life. Some of you may not have kids, but hopefully you will find it within you to understand what other people are going through. And I know everybody has a lot going on right now. My thing happens to be that I have small kids at home a lot while trying to work and teach and do all the things that need to be done, and make lunches and host Halloween parties and make Halloween costumes and do all of the stuff. Okay, so this one I'm not really going to test you on, but I want you to know exists. We have these two planes moving relative to each other. We'll look at the way this deforms. It's really kind of the same as saying I am pulling on this side or squishing this side. Look, it moves the exact same. It's the same thing as when I sheared these two sides relative to each other. So really, we're saying shear forces are very similar to principal forces that move like that on a 45-degree axis. Bending is the force that causes tension on one side and compression on the other. So if bending can be related to compression and tension, we can probably still make use of those axial stress strain curves that told us what the modulus of elasticity was, what the yield stress was, what the ultimate stress was, and what the strain was at those values. So if we know those things exist for axial, and say we knew that the yield stress of steel was 350 MPa, which I told you it is. If I am bending this object, and we know that deformation or strain is related to stress. You increase the stress, you increase the strain. What parts of this are deforming the most? Look at the little squares on this. They're perfectly the same, and now we're moving it. It looks like the most deformation happens right here. It's squishing here and stretching right here. So the very top and the very bottom are where we're seeing the most axial deformation. Well, we call that the extreme fibers, or the top and the bottom is the extreme fibers. So it looks like we would care that the extreme fibers of this in bending don't exceed their maximum stress, or 350 MPa. So we can relate that to tension and compression, and we don't want to exceed the maximum compression and the maximum tension in that object. So things we won't talk about: the shear stress equation. V is really stress times area. Bending stress equations, where M, or moment, is stress times S, where S is the section modulus. Look at this though. We had an equation for axial where P equaled stress times area. Well, area is about the shape of the object. What if I told you that if you stick around and do the graduate course with me, we'll derive S and we'll find that it is about the shape of the object. So really, if we know the shape of our object and we know the maximum stress something can see, we could figure out the maximum moment. If we know the shape of the object and the maximum stress an object that material can see, we can figure out the maximum shear it can take. And we've already seen that if we know the shape of the object and the maximum stress it can see, we can figure out the maximum force that object can take. Which, remember, the maximum force an object can take is what we care about. We want to make sure that that maximum force an object can take is greater than the actual force that it takes. So, forever tips. Stress and strain relate to strength and stiffness. Stress and strain are related to each other through modulus of elasticity. You should know the equation for stress. You should know the equation for strain. You should know the modulus elasticity and the typical steel values, and you should know what the steel and concrete stress strain curve look like. So that's all we're going to talk about today. Going forward in the next few weeks, we're going to start to look at the stress and strain of each material and see what that does for us. How can we put that into something? I am giving you these equations for shear and moment, and we've already talked about axial loads. And we're going to start to figure out what those maximum forces our different materials can see or experience for different shapes of objects. And so we're getting so close to having actual answers and knowing, does this object work? Does this object work for this applied load. And knowing what the extreme fibers see starts to be really important. Okay, see you next week, team.